This particular piece of code is designed to extract the information from the open column within a data frame titled diff and assign it to a fresh variable labeled as data. Following this step, the values attribute is utilized to convert this information into a NumPy array, which is then held in the variable dataset. Next, the code proceeds to determine the size of the training data by taking 80 of the total dataset length and rounding it up to the nearest whole number using the math function. This is a widely adopted approach in the realm of machine learning, where typically a section of the data is earmarked for training purposes, typically constituting 80 of the dataset. The size of the training data plays a critical role in numerous machine learning algorithms, where it is vital to divide the dataset into distinct training and testing sets for the evaluation of the model's effectiveness. By employing this code snippet, it guarantees that the appropriate data volume is designated for training, thereby enhancing the machine learning model's overall performance. The provided code snippet serves as a foundational framework for constructing and training a long short-term memory LSTM neural network model tailor-made for time series forecasting, specifically when applied to predicting stock prices. Here's a breakdown of the code's functionality. 1. It includes essential libraries like Math, NumPy, Pandas, and Pandas DataReader for efficient data management and computations. 2. It utilizes min-max-ler from scikit-learn to standardize the dataset. 3. It incorporates sequential, dense, and LSTM modules from Keras to establish the LSTM neural network structure. 4. It integrates the matplotlib, pyplot library to facilitate visualization of outcomes. The significance of this code lies in its utilization of NumPy and Pandas for data manipulation, leveraging Pandas DataReader to fetch stock price data dynamically, employing min-max-ler to normalize the data before inputting it into the neural network, utilizing Keras for simplified neural network design, especially effective for sequential prediction tasks like time series forecasting, and employing matplotlib to create graphical representations of the data and model forecasts. In essence, this code snippet establishes the essential groundwork and tools required to construct an LSTM model tailored for predicting stock prices accurately. The following code snippet initiates a variable called ticker and sets it equal to Amazon. In this scenario, Amazon probably denotes the stock symbol for a specific company, namely Amazon Inc. This programming excerpt serves as a straightforward instance of initializing a variable. By defining variables in this manner, we can conveniently retain and employ values across the program without the necessity of repeatedly embedding them. Here, the ticker variable retains the stock symbol, enabling its utilization in subsequent sections of the code to monitor details associated with that particular stock. The following code snippet sets the variable ticker TSLA. This line serves the primary purpose of storing the value TSLA within the variable. Assigning values to variables lies at the core of programming. Think of variables as label bins that can store various kinds of data to be used and modified across the program. In this scenario, the variable ticker might hold the stock symbol for a specific stock, aiding in monitoring or fetching data linked to that particular stock symbol as the program unfolds. All this piece of code does is set the variable ticker to hold the value Uber. Working with variables lies at the core of programming. It enables us to save and recycle data values across our code. Here, the variable ticker is employed to preserve details connected to the stock ticker symbol representing Uber. This is handy for referring back to this detail later in the code without needing to rewrite the value repeatedly. This piece of code sets up a variable named ticker with the value TSLA, denoting the stock ticker symbol for Tesla Inc., a widely known electric vehicle company. Stock tickers, unique symbols designated to businesses trading publicly, serve for identification and trading activities on the stock market. Within this context, the variable ticker stands as a representation of Tesla Inc., a stock symbol within a software application or script. This facilitates the performance of various tasks concerning the company's stock, like retrieving stock information, assessing patterns, or aiding in investment choices. By initializing the variable with the stock symbol TSLA, the code gains the ability to easily access and manipulate data related to Tesla Inc. as stock throughout its operations. The following snippet of code fetches historical stock price information for a particular stock symbol from Yahoo Finance by utilizing the data reader function within the Pandas library. It sets the commencement date as January 1, 2012, and the conclusion date as May 24, 2020. The data reader function simplifies the task of extracting data from various online sources, such as Yahoo Finance. This function streamlines the process of accessing datasets without requiring the manual downloading of files, ensuring efficiency. Subsequently, the data retrieved is formatted as a pandas data frame, ready for in-depth analysis or manipulation. In essence, this code snippet acquires historical stock price data for a specific stock symbol from Yahoo Finance within the designated timeframe by leveraging the pandas data reader feature. You can utilize this snippet to fetch the dimensions of a data frame in Python by employing the shape attribute. This attribute furnishes a tuple that showcases the quantity of rows and columns within the data frame. In practical terms, if the shape attribute yields 5, 3, it signifies that the data frame encompasses 5 rows and 3 columns. Being aware of a data frame's dimensions is significant as it empowers us to gauge the scale and layout of our data, which is pivotal for engaging in data analysis and manipulation tasks. This insight is instrumental for efficiently processing and scrutinizing the data. In this line of code, the matplotlib plot style is being configured to dark background. Incorporating this code will render the plots with a dark backdrop, enhancing the visibility of data points and lines. This adjustment proves beneficial for data demonstrations and presentations or reports, as well as for tasks in dimly lit surroundings. Customizing the plot style is instrumental in enhancing data presentation and elevating the visual appeal of the plots. Furthermore, it facilitates the focus on specific data facets by modifying the color palette and backdrop settings. The following script serves to create a line plot that illustrates the closing price information extracted from a data frame labeled diff. The process is as follows. By executing pult, figure fixes a 16:8. A fresh plot with dimensions of 16:8 inches comes into existence. Pult, table closing price designates the plot title as closing price. Pult, plot flows charts the closing price details from the data frame onto the graph. Setting the x-axis label to date and y-axis label to close price cust with a font size of 18 is accomplished through pult. Clibble date, font size 18 and pult, style below's price cust font size 18 respectively. The plot is exhibited by invoking pult. Show. This piece of code proves beneficial in visually examining and dissecting the fluctuation in closing prices over a period. Visualization plays a pivotal role in unraveling trends and patterns, offering valuable insights that aid in making well-informed decisions across diverse sectors including finance, research, and more. This snippet of code seems to be a crucial part of a dataset manipulation process. Let's delve into what this code accomplishes initially. The code snippet datav filter close narrows down the data frame diff to contain solely the close column, focusing on the closing prices of the dataset. Next, the line dataset data values extracts the values from the close column and encapsulates them in an array named dataset for subsequent processing. Afterward, training data on math LN dataset 8 computes the extent of the training data by securing 80 of the overall dataset length. This ensures an ample amount of data points for training a machine learning model, as it's conventional for training data to make up 80 of the dataset. The training data variable retains the training data's length, presumably to be utilized in later stages to divide the dataset into training and testing sets effectively. In essence, this code snippet executes filtering on a data frame to select a specific column close, transforms that column into an array, determines the required length for the training data, and stores it in a variable. Such procedures are typically essential in data preparation for machine learning or statistical analysis, ensuring a proper division of data for training and testing purposes. Utilizing min-max scaling on a dataset is a common practice in the realms of machine learning and data processing to standardize data within a specific range. The mechanism of min-max scaling involves adjusting the data so that it fits within a designated range, often set between 0 and 1. This is achieved by first subtracting the minimum value from each data point and then dividing by the total range of values within the dataset. Within this code snippet, a min-max scalar object is instantiated, specifying a desired feature range of 0 to 1, which will later be employed to scale the dataset. The dataset is then scaled using the fit transform method of the scalar, which leverages the minimum and maximum values present in the dataset. Preceding the input of data into machine learning algorithms, scaling is crucial to ensure each feature holds equal weight during the learning phase. mitigating the risk of certain features overpowering others due to their larger scales. Min-max scaling contributes to standardizing feature ranges, bolstering model resilience, and ultimately enhancing performance. This excerpt is a crucial segment of a data preparation procedure intended for training a time series forecasting machine learning model. Here's a breakdown of its functionality. Initially, a subset of the scaled data is assigned to trained data, accommodating the data slice designated for model training, ranging from the first index to training data. Two empty lists, cotrain and utrain, were set up to host the input and output training data correspondingly. A for loop is employed to iterate over trained data, commencing from the 61st element since a 60-item lookback window is utilized. This iteration spans from index 60 to the end of trained data. During each iteration, a sequence consisting of 60 prior data points is crafted as input utrain, while the subsequent data point serves as the output utrain. These sequences are then appended to their respective lists. The conditional statement within the loop serves the purpose of displaying the training data from the first iteration. This step aids in comprehending and validating the data transformations effectively. In time series forecasting tasks, input features X are typically engineered by leveraging a historical window of time steps. The model is trained to anticipate the subsequent time step Y. Segmenting the data into input-output pairs facilitates the model in grasping the data patterns and correlations, enabling accurate predictions. This methodology is pivotal for constructing precise and efficient machine learning models tailored to predicting future values within a time series dataset. The given code excerpt transforms the variables cotrain and utrain from lists or similar iterables into NumPy arrays. This switch is crucial as NumPy arrays are finely tuned for mathematical computations, delivering superior performance in contrast to standard Python lists. Through this conversion to NumPy arrays, we enable ourselves to leverage the array functionalities and broadcasting capabilities that NumPy offers. This, in turn, enhances the speed and efficiency of our code, especially when handling substantial datasets. The provided code snippet modifies the structure of the training data train by appending an additional dimension with a size of 1 at the conclusion, ensuring the total number of elements remains unchanged. Following the reshaping process, the code proceeds to display the resulting shape of the utrain array. This type of code is commonly utilized within the realm of machine learning, particularly when dealing with input data that is expected to conform to particular shapes or dimensions. Such data manipulation is often imperative for various types of neural networks or machine learning algorithms that mandate inputs to be presented in certain configurations, such as 3D convolutional neural networks. The following code snippet demonstrates the construction of a long short-term memory LSTM neural network model through the Keras library. Each line plays a distinct role. 1. To kick things off, model sequential initiates a sequential model, essentially a linear stack of layers. 2. Model LSTM returns sequence true. Input shape X train. Shape 1 incorporates the initial LSTM layer into the model. This first layer consists of 50 units and is tasked with generating sequences output for each time step based on the specified input shape, ideal for sequence prediction purposes. 3. Another LSTM layer is introduced with model LSTM returns sequence files, comprising 50 units. Setting return sequence files instructs the layer to produce solely the outcome of the last time step, rather than each time step's output. 4. The introduction of a fully connected dense layer with 25 neurons occurs via model dense 25. This layer processes the output stemming from the LSTM layers. 5. Finally, a companion dense layer equipped with a single neuron model dense concludes the architecture by serving as the output layer responsible for delivering the final prediction. Leveraging LSTM layers is imperative for managing sequence data, proficiently capturing prolonged data dependencies. Such a design proves paramount for tasks where the data's sequential order holds significance, such as time series forecasting or endeavors within natural language processing. In essence, this code snippet effectively crafts an LSTM neural network model blueprint tailored for addressing sequence prediction challenges. In this code snippet, we're setting up the neural network model for training. Let's break down each component. 1. By setting the optimizer parameter to atom, we're instructing the model on which optimization algorithm to leverage during training. ADAM, short for Adaptive Moment Estimation, stands out as a favored choice in the realm of optimization algorithms. It excels in adjusting the network weights efficiently by considering gradients dynamically. This adaptability makes it a prime candidate for driving the training of complex deep learning models. 2. The choice of setting the loss function to mean squared error dictates the metric to utilize during training. Mean squared error emerges as a standard pick for scenarios involving regression tasks. Its core aim is to minimize the square variance between predicted and true values. Throughout training, the model will strive to lower this specific loss function. Through these defined configurations, the model will undergo training employing the ADAM optimizer to reduce the mean squared error loss function. This groundwork is imperative for orchestrating the training phase effectively and detailing how the model should distill insights from the data to furnish precise predictions. This snippet of code serves the purpose of instructing a machine learning model during its training phase. Let's break down each parameter. HuTrain. It represents the input data utilized to train the model. TTrain. This refers to the target data crucial for training the model. Batch size. This dictates the number of samples processed per gradient update, with a batch size of 1 implying that the model is updated after each individual sample. Epochs. An epoch involves a single pass over the complete training dataset. This parameter determines how many times the learning algorithm will iterate over the entire training dataset. When model fit is invoked, the machine learning model undergoes training based on the designated training data HuTrain and UTrain for a total of 3 epochs, utilizing a batch size of 1. Consequently, the model adjusts its weights after handling each individual sample within the training dataset for 3 complete runs across the dataset. Training a model stands as a critical phase in the realm of machine learning as it aims to fine-tune its parameters and comprehend the underlying patterns within the training data to facilitate precise predictions on novel, unseen data. The fit function operates by refining the model's weights through the minimization of the stated loss function on the training data via optimization techniques like stochastic gradient descent or ADAM. In this code snippet, we're setting up the test data for a machine learning model to anticipate future values by forming data sequences. Firstly, the test data variable grabs the most recent 60 data entries from the scaled dataset for testing purposes. Then, it initializes 2 empty lists, ctest and utest. The utest list gets filled with values extracted from the original dataset that match the data points following the training data. Next, a loop runs through the range starting from 60 up to the length of the test data. During each loop cycle, a set of 60 elements is selected from the test data and added to the ctest list. These sequences are specifically drawn from the initial column of the dataset. This piece of code plays a vital role in structuring data correctly for training models focused on time series forecasting, like an LSTM neural network, by crafting data sequences of a fixed length. In this case 60, the model can grasp underlying patterns and correlations within the data to generate predictions based on past values. This preparatory stage is essential for the model to interpret input data effectively and make precise forecasts based on historical trends. The code snippet transforms the variable test into a NumPy array by utilizing the NIP array function from the NumPy library. This conversion enhances the efficiency of data manipulation in test as NumPy arrays offer native support for various mathematical operations and are more flexible compared to standard Python lists. Through this conversion, you unlock the potential of NumPy's broadcasting features, element-wise computations, and additional functionalities that streamline the handling of multidimensional arrays and extensive datasets in scientific computations and data analysis assignments. The provided code snippet is designed to restructure the ctest dataset to align with the specific requirements of a machine learning model. In essence, it transforms the ctest data into a format where it has dimensions specified as samples, time steps, features. Initially, it assumes that the ctest data is in a 2-array format. During the process, the data is adapted so that the number of samples and time steps remain unchanged, while a new dimension is introduced with a size of 1 to represent the features. This type of data manipulation is commonly necessary when dealing with particular neural networks like LSTMs, which anticipate input data to exhibit this 3-dimensional configuration. Ultimately, this code segment readies the dataset for utilization in such models by configuring it into the requisite input structure. The code snippet provided serves two main purposes initially. The model utilizes the input data dataset to generate predictions, forecasting the values based on the input received. Subsequently, the code executes the scalar inverse transform prediction step to revert the scaling adjustments previously applied to the forecasted results. This step is vital in scenarios where the data underwent preprocessing or scaling before the model training. Reversing the scaling process enables the predictions to be converted back to their initial scale, enhancing their interpretability and enabling their use for further analysis or assessment. Fundamentally, this piece of code plays a critical role in restoring the predictions to their original form, facilitating a more insightful and practical interpretation of the model outcomes. This script computes the root mean squared error by comparing the predictions to the actual values you test. Essentially, the code performs the following steps. 1. It calculates the differences between the predictions and the actual values you test. 2. Squares these differences. 3. Computes the average of the squared differences. 4. Finally, it takes the square root of the average to obtain the RUMs. RUMs serves as a widely employed measure for assessing a machine learning model's performance. It gauges the average squared deviations between predicted and actual values. A lower RUM signifies a closer alignment of the model with the data. In this context, the script plays a crucial role in assessing the predictive accuracy of the model. In this code snippet, the matplotlib library in Python is utilized to visualize data with the dark background style. By employing this style, the plot adopts a dark backdrop with light-hued lines and markers. This approach proves beneficial for creating visually captivating data presentations, particularly if the standard style doesn't align with the setting or audience's preferences. Opting for a distinct style such as dark background can enhance plot legibility, appeal, and presentation appropriateness. Moreover, it effectively accentuates the plotted data by introducing a sharp contrast between the background and the visual elements. This specific code excerpt seems to form a segment of a script focused on analyzing time series data linked to stock prices. Specifically concerning Amazon shares, here's a breakdown of the script's functionalities to begin with. The code segments the provided data referred to as data into two segments: train and valid. The train portion is utilized for training the machine learning model, while the valid segment is reserved for validating or testing the model's efficacy. Next, the machine learning model generates predictions based on the valid data and appends these predictions to a novel column labeled predictions within the valid data frames. Subsequently, the script leverages matplotlib to craft a visualization. The resulting plot showcases the actual stock prices gathered from both the training and validation data sets, alongside the projected stock prices generated by the model for the validation data. Within the plot, you can anticipate observing actual close prices stemming from the training and validation data exhibited in red and yellow colors correspondingly. Anticipated close prices arising from the model for the validation data showcased in green, a visual key providing clarity on which line corresponds to each dataset. Conclusively, the visualization is stored as an image file baptized prediction, pane, and then showcased to the observer. By utilizing this code, we can efficiently juxtapose the model's forecasts against the factual stock prices noted in the validation data. Such a comparison facilitates the assessment of the model's performance, enabling insights into its accuracy and areas that might necessitate enhancement. In addition, the visualization simplifies the communication of the model's effectiveness to stakeholders or team members. This snippet of code probably pertains to a function or method designed to fetch the final 15 elements from a data structure or a collection. It is versatile and can be applied to arrays, lists, or other data structures for accessing a selection of elements from the conclusion of this sequence. This becomes handy when you require only a segment of items from the tail end of the collection for subsequent examination or manipulation. Extracting the tail end of the data allows you to concentrate on a particular subset without needing to handle the entire dataset, thereby potentially enhancing efficiency in processing speed and memory utilization. The following code snippet aims to forecast the stock price of a designated ticker symbol for the upcoming day. The process involves several key steps. Initially, it fetches the stock information for the provided ticker symbol from Yahoo Finance within the designated time frame. Subsequently, it refines the acquired data to retain solely the close price entries. The subsequent action involves normalizing the most recent 60 days of closing prices utilizing a specified salary. It then readies the information for prediction by reshaping it and forming a NumPy array. This processed data is then fed into a pre-existing model for predicting the succeeding day's stock price. The forecasted price is subsequently converted back to the original scale through inverse transformation. Ultimately, the code displays the projected price for the following day for the chosen stock ticker. This code segment proves beneficial for financial scrutiny, algorithmic trading, or forecasting stock prices for investment strategies. It helps in streamlining the procedure of forecasting stock prices based on historical trends and machine learning algorithms, offering a valuable resource for traders and investors alike. This excerpt is a snippet from a program designed to forecast the opening stock price of a specific company the following day by leveraging historical stock price data through machine learning, likely a neural network model. To sum up the code snippet 1. Utilizing the data reader function, historical stock price data from Yahoo Finance concerning a designated company identified by ticker symbol is obtained. 2. The code specifically extracts the open price data from the stock information. 3. It filters out the most recent 60 days worth of open prices and standardizes these values for prediction purposes. 4. The standardized open prices from the last 60 days are adjusted to meet the model's input criteria. 5. The adjusted input data is fed into the model to forecast the opening price for the subsequent day. 6. The forecasted price is then converted back to its original scale to determine the actual predicted stock price. This type of coding is instrumental in financial predictive analysis, a powerful tool for anticipating stock prices. By training a machine learning model on historical stock data, we can generate forecasts on future stock prices. This capability is beneficial for traders, investors, and financial analysts seeking to make well-informed decisions.